there, plus pay these, plus additionally so much of other trouble, is that visa, everything. Nothing here.
Okay.
I mean, you can just watch anytime, whatever you like, whoever. I mean, whatever is interesting session, you sit and you you don't have to go anywhere, and you can hear that person so directly. You can ask questions so directly. So that way, it was very useful.
So
I
it's
also told
and
my students to attend all of these things, so they were also very happy.
yeah. I think we are on live on YouTube now. So we start.
Yes,
Yeah.
anytime you tell me.
Yeah. So I welcome all of you for the fourth lecture on the online series organized by the Department of Physics of KJ Somaya College of Science and Commerce and IIPT Mumbai Sub-Regional Council. So as you know, this is the fourth lecture in the series. First lecture was given by Professor Joseph Samuel, second by Dr. Ahmed, third by Dr. Adul Modi, and this we have another exciting lecture in this series by Dr. Sri Ganesh Prabhu. So we start with this. I'll just give all of you all a virtual tour of the Somaya campus, and then can I'm not able to see the screen. Thank you very much. And now I would like to call upon Mahesh to do the introduction of IIPT.
Good evening, everybody. Uh, the IIPT, or Indian Association of Physics Teachers, was founded in 1984 by motivated teachers like Professor Khandelwal and a group of other motivated teachers. The sole aim of founding this was to improve the teaching learning level of physics throughout the country. IIPT has been conducting two voluntary examinations, one at undergraduate level, a national graduate examination in physics, and one at plus two level, which is called NSE examination, National Standard Examination. The examination was so widespread and the quality was maintained, though it was voluntary examination, and quality was maintained such that when India decided to participate in national international Olympiads, they decided to choose this NSE examination as the first level examination. So NSE examination was not really started for Olympiad purpose, but it has become the first step for going to an international Olympiad. Under IIPT, there are various regional councils. So we have Maharashtra Regional Council. Under that, we have Mumbai Sub-Regional Council. And Mumbai Sub-Regional Council, sticking to the original aim of IIPT, is conducting various kinds of programs where teaching learning can be improved in the society. As part of its programs, we conduct various, every year, a summer school where we basically address the things which are missed out from the syllabus, and instead of complaining, we say, let us do these things so that students who are interested can, when they graduate, they develop required skills properly. Apart from that, there are various courses and seminars for teachers as well at both junior college level and degree college level. We have also recently started, after this pandemic, we started online lecture series. First lecture series was in collaboration with Junjunwala College, and the second series is now in collaboration with Somaya College. And we have also started our YouTube channel. So I request all of you to subscribe to YouTube channel also. Mumbai, you can in YouTube channel, you can just type IIPT Mumbai, search for IIPT Mumbai YouTube channel, and you can subscribe to those. Okay, thank you. Keep attending our programs. We will be getting different announcements on our Telegram group. We'll be putting the Telegram channel link also in the chat in some time. Okay, over to Shekhar.
Thank you, Mahesh. Now I would like to call upon Ketan Gaikwad to introduce our today's speaker. Ketan.
Good evening, one and all. It gives me great privilege to introduce our today's resource person, Dr. S.S. Prabhu. He completed PhD in physics from TIFR. Currently, he is working as Associate Professor of Physics at Department of Condensed Matter Physics and Material Science, TIFR, Mumbai. His research field includes ultra-fast time-resolved phenomena in materials, terahertz spectroscopy of materials, metamaterials, high-field terahertz and near-field terahertz microscopy. He has more than 52 research papers in international journals and several articles in many magazines. He has several invited talks. This is brief introduction about today's resource persons. I welcome you, sir, for today's lecture. Thank you. May I hand over to this Shekhar, sir?
Thank you, Ketan. On behalf of Department of Physics and IIPT, I would ask Dr. Sri Ganesh Prabhu to please take over the session.
So thank you. Good evening, all of you. And I wish to thank Professor Mahesh, Professor Shekhar, and Professor Gaikwad. Thank you for your very kind invitation and all the arrangements. It has been a very nice and a great pleasure to be with IIPT. When I was a student in Mumbai studying physics, that time I used to also attend IIPT lecture. I mean, IIPT used to arrange some lectures, and I used to. It was very beneficial to me. And I'm also very happy to see Professor Bharat Kamgude and many other people from other parts of Maharashtra who have been able to join because of this online feature. And I welcome all of them. And thank you so much. It's a great pleasure to be here and talking to all of you. I will share with you some of our excitement. So as Professor Mahesh told me, Mahesh Shetty told me that there will be also a lot of undergraduate professors who will be also attending this. So I have kept it at a level where it is not going to be far too technical. but we will also tell you what kind of things that we are doing, what is exciting. At the same time, what are the other exciting things that you can do, and that way you will get some idea as to how you can also contribute being in your own institution, whether it's a college or junior college or whatever. But if you are really passionate about doing something with the computer at hand, also you can do certain wonderful things. So as I will go ahead, I'll explain you some ideas. You might find something which are very useful to you, and you might find them very exciting. And I hope that at the end of the lecture, you will get some idea about this. So my main subject is a little different. We do ultrafast spectroscopy, where we use lasers for very fast to study very fast phenomena. But today I won't be talking about any of that part. I will basically tell you something about how photonics subject itself has come up. So as you already know that the beginning of the 20th century was for basically electrons, because electron was just figured out by J.J. Thomson, and then by the end of 1890s, and then it was beginning of 1900s. Lot of people have been using a lot of applications of this, and they realized that all these currents are happening because of electrons. And these electrons actually dominated the next 50 years or 70 years of that progress. And using these electronics, basically people develop a lot of applications spanning everything that you can name it. And towards the end of the 20th century, around 1990s or 2000 or so, a lot of photon related applications emerged. So now you had an electron getting replaced by a photon. And now I can tell you that the 21st century will be dominated by the photons and the related applications. So basically, what is photonics? Photonics, just like electronics deals with electronic things and electrons, photonics deals with controlled production, evolution, and detection of mainly coherent light photons. So these mainly coherent light photons come from the lasers, which you already identified. And within this optical region of the electromagnetic spectrum, what you call it as a vacuum wavelength from 50 nanometer going to 5000 micrometer. So we work also in the 5000 micrometer in that region. So that I will talk about little towards the end of the talk. And if you look at the photon energies, these energies in electron volts go from 25 electron volt down to 2 milli electron volt or even 0.2 milli electron volt. So that's very, very, very small energy of a photon. So I mean, you may wonder what kind of use many of these will have, but you will see that there are so many different uses, and we are constantly bombarded by all these different types of radiations. Some of them are completely unknown to us. So with the advent of laser, a lot of nonlinear properties and of optical media also became quite what people started exploring, and that actually opened up a completely new field. So in photonics, you will basically have lasers, linear optical medium. This is the one which you normally use. And now with the laser, you also have a nonlinear optical medium where red light will convert it into blue light, or green light, or infrared light gets converted into green light, and all these kinds of magical things one can do. You also have different types of sources and photodetectors which you can generate. You also have what is known as a non-classical light. Of course, there is not enough time to talk about many of these. The non-classical light, which light, even after scattering, it will just still remain the same. It will keep itself the same state. Or you can focus it very tightly. That there are certain kind of light it will not have any dispersion. So all these kinds of things one can do. And now people are also getting into quantum light. Basically, it's a photon, and that can be used for quantum communication. And these base things can be used for quantum computing and all that. So a lot of those applications are there. I will basically in this talk limit myself to sort of metamaterials, plasmonic, and terahertz spectroscopy, which is what we do. And because that will give you some flavor as to what are the things that one can do in India, and which are accessible to many of you people. because you know that somebody is working in that, and you can also contribute in your own way. So basically, terahertz is having like 300 micron kind of wavelength. It's an infrared one. So we will talk about it, but towards the end. So you see, this is the first photograph of this ENIAC, which was made with 18,000 vacuum tubes. This is the computer size. And as the transistors were invented in 1947, by 1950s or 54, you could see that this entire room that was filled with by this computer now suddenly became filled just by with three cupboards. And now the mobile that you are having in your hand is at least 1,000 times powerful than this machine which is shown here. So you can see, as the number of transistors grew, there were multi-core CPUs came up, and because of this semiconductor development, we had a huge amount of revolution, and you are constantly seeing this evolution taking place in our life, and it is going to pervade our life far too much. So this is a VLSI circuit. You can see there are almost a billion transistors, and there is no way you can there are very advanced techniques to even figure out if there is any defect in this. And even the lines which run through, which carry these signals, are of the order of 25-30 nanometers. So they have also got reduced to a small place. So people are actually now talking about these optical integrated circuits, where you have a source, you have a beam splitters, you have detectors, and you have different units, and these will the electrons at least have some finite speed, but here these will just run in a fraction of a second, because they will run with the speed of light. So these will be extremely fast moving working circuits. So people are now getting into these type of things, and you can see that I'll explain to you what are these structures and why do they look somewhat weird. Because of course, you are manipulating light, means you need different kind of ideas compared to if you are manipulating electron. So electron has been replaced by photon. So naturally, those devices will be replaced by photon related devices. So where are the applications in photonics? You have telecommunications for down converting to microwave, optical fiber communications. You have medical applications where laser surgeries, eyesight corrections, tattoo removal, surgical endoscopy, a lot of things are there. Manufacturing processes in industries, they involve use of laser in welding, cutting, drilling. You can get all different kinds of beautiful shapes. You also use them in building and construction, where you can generate the smart structures, and laser range finding, laser leveling. And space exploration and aviation also has huge use in the astronomical telescopes. Military though just loves it, because you have full command and control based on these optical things, because there's a very short delay, and because of these very fast operating displays and scanners and sensors, because there in split second you have to act. So these are very highly demanding circuits and units. So you can use now people have gone to the level of making even laser cannons and all that. People also use it for metrology, such range finding, then frequency and time measurement. So this is another thing, you can do extremely high precision measurements using this. And people are now also going towards this photon computing. So already about 20-30 years back, they showed the optical computer, but now they are using this to go for quantum computing. So that's another part. And now you have microphotonics and nanophotonics, because you are miniaturizing everything. And when you miniaturize to a nano size, then the light behaves very, very differently. And that also I will give you some examples just to give you some idea. So this is the typical photonic circuit that you can see how it looks. It looks little weirder than the normal thing, and you can also see its small shape, that it is at the top of the tweezer being held. And you can use this for fiber network converter, so 10 to hundreds of gigabytes. So there was this how much packaging that you can do, how many devices you can put per chip. And you can see this is a logarithmic graph which was going almost straight for electronics with over billions of transistors into this our Intel RAM. But photonics has been a very slow rise. There was already of the 10 raised to 7 orders difference, but this is also picking up, and pretty soon this will stop and this one will take over. That's what people are thinking. So laser was actually invented by two people, Professor Arthur Shallow and Charles Towns. So this is the photograph of him. And when they invented this laser, there's a lot of incredible laser, and a lot of magazines showed that it is already having a war and all that. And so he said, ki, if you really want to see the credible laser, please see inside his lab. So this is what he had put. So you can imagine. Now, of course, we have come quite far away from that. Now you have very compact solid state lasers. These are all of different types: gas lasers, liquid dye lasers, semiconductor lasers. These are the most miniature ones and extremely powerful also. And because of this technology development, you have these put up in many different gadgets, and because of that now you can do virtually anything that is possible. uh, Lasers are used for in material research also. So you have cutting, drilling, micro machining, welding, engraving, data processing, thin film development, lithography, and time resolved phenomena. So I work in this time resolved phenomena area. So I mean, you can see there are so many different applications. This Dr. Rangaswamy Srinivasan from IBM Research Lab was the first one to do the surgery, use the laser for surgery of the eye, and he was felicitated by. He is an American citizen now. So this is our first Indian connection. He was given President's Medal for this achievement. And then this is the CO2 laser, most famous one used for cutting kilowatt. And this is Professor CKN Patel, Chandrakumar Narayan Bhai Patel from Bell Labs. So this is his laser. You can see he's standing with. And currently, this entire thing has been miniaturized to a very small place, very small size. I'm almost 10 times powerful. And you can see that it can actually cut different steels. It can do carvings, metals, micro machining. Even diamonds can be cut using that. And people have also used it for etching, engraving into different things. So you can see, you can actually focus it very tightly, and you can create these different patterns. And you can see these are all periodic sort of very specific patterns. So these are can be used as one and zeros. So this can be used for saving the data. And as you can see, previously when we were in college, used to have, not college, I mean almost 10, 15 years ago, CD was very popular. Then came DVD, and now you have Blu-ray. So as the progress was made in the semiconductor laser, so we went from 780 nanometer to 650 nanometer to 405 nanometer, which is the blue laser. The Nobel Prize goes to Professor Nakamura for this gallium nitride based blue laser. Is because just from CD to Blu-ray, I mean, you can see this is the ACM picture of the CD versus the Blu-ray, and you can see the huge amount of things that can be stored in this, the amount of data that can be stored, because the spot size becomes very small. So this has created a big revolution. And also these lasers, which have become very powerful, they are also their pulses are quite small. So here are the different time zones in which we work. So this is for materials research that we do. We study material interaction, and you can see femtosecond is 10 raised to minus 15th of a second, picosecond is 10 raised to minus 12, nanosecond is 10 raised to minus 9, microsecond is 10 raised to minus 6. So photon absorption takes place much shorter period in the femtosecond, and then between femtosecond to picosecond, you get all these delocalized of phonon modes, excited anharmonic modes, etc. So you can study this part. So this is the part that we look at. And then between picosecond to nanosecond, you start seeing the equilibrium distribution of these states. and all these electrons and carriers and everything. So all these different things one can study, and then the final melting vapor generation, and you say that the laser shot has ablated the material and all that. That takes is a very very slow process, and that takes of the order of microseconds. So microsecond is too much delay for us. I mean, it's too slow for us. However, microsecond is 1 millionth of a second. So you can imagine the scale at which we work. So laser deposition of thin films is a very common thing. So from solid, you can directly get into the gaseous form because of this huge plasma generation that takes place. Because this laser field actually concentrates and throws out the material, and then this material gets deposited on the substrate, and you can form actually a very nice pristine thin film. So there are many groups in the world and even in India who can actually grow these very nice thin films by laser ablation. In our group, so Achanta Venugopal, he had done these many of these wonderful laser-based nano patterning. So you could actually focus this laser light with different exposures at two different polarizations. I mean, at 90 degree with respect to each other, and you can actually generate a very nice square pattern of holes, or this is a different kind of pattern that you can do. You can see it's a sort of a periodic pattern, and using this, one can study different kinds of band structures. So that I will explain to you how this part can be done. One can also use this for the second harmonic generation, and we have done this also quite routinely now because of high power laser that is available with us. And once you put it on a particular crystal, you can actually generate what is known as a white continuum. White continuum means you can generate all colors of the light. So you can see here from red to violet, all lights have been generated just by focusing one single 800 nanometer, that is a sort of near infrared light that we focus here. With our laser, we are able to actually generate such a light. So we use these kinds of light to excite the sample, and then either look at reflected light or transmitted light, or some luminescence or fluorescence that comes out of this. So based on that, we have absorption, transmission, reflection, or fluorescence spectroscopy, and this is how the sample actually luminesces. And we also go one part further where we would like to actually study this as a time phenomenon. So for that, what you need is you need a pulse of the laser. So this is the Heisenberg uncertainty principle, that if your time pulse is quite broad, then your frequency, in frequency, the spectrum becomes quite narrow. But if you have a very narrow or very short time, like in hundreds of femtoseconds, then your frequency, that is the energy spectrum, becomes quite broad. So either you can have very sharp time resolution, but then you lose energy resolution, or you can have a very low time resolution but have very sharp energy resolution. Normally, the static experiments that people do just with CW laser or helium neon laser or something, those actually fall into this category where the frequency is very, very sharp at say 632.8 nanometer wavelength emission, and your time is very, 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 very broad. So I mean, several nanoseconds. So you don't really look at particular phenomena. You just look at the static thing. So we use, of course, the femtosecond laser. So what happens is you can see that different color are emitted by this incident light because of some different phenomena that is occurring in the sample. And what we do is we call the excitation pulse as the pump beam. So that one actually creates carriers here, and then the actual action starts. And then we put another incident light pulse to look at the reflected or transmitted pulse and see how that gets modified as the effect of this pump beam. And this actually, as we go on changing the delay between the incident, this pump beam and the incident pulse, you can actually probe different phenomena. So that is called time resolved transmission or reflection or fluorescence spectroscopy. So these are the pulses of light that we put in. And using that, you can monitor, how a particular, here actually I'm showing you something like what is known as an exciton evolution as a function of time. And here you can actually see these. I don't know if this animation is visible to you, but you can see that they are wobbling to and fro, and these are stretching to and fro, and these kind of oscillations you can actually monitor as a function of time in picoseconds. So this is something, these are called phonon vibrations, and which you can actually observe in real life. So there's wonderful things one can do. So lasers are basically miniaturizing, their colors are changing, and now you have started even using it in your I don't know how many of you use this band, but I'm sure many of you people use this band while running and jogging and all that. So it has this basically green laser which actually monitors all your parameters, and they are displayed here. So we will see how these things happen. So they are basically coming into our live daily life like this. Then we come to what is known as metamaterials. So these are the materials which do not exist in nature. So you have to artificially create them. So this is for the kind of wavelengths that we work on. This is a work of Professor Sridhar from US. So what he did was he basically created these typical electronic boards he took, and he created these which are called split ring resonators. And then he put all these rods, everything, this periodic array in 2 dimension, 3 dimension, and then you can actually pass these long wavelength light through this, and you will actually see that it is behaving very differently. Say, for example, this rod, these undergoes this kind of refraction, but you can also get a negative refraction. So now you see, this is typically how the refracted light will look at, but here you are seeing it in opposite. So these are the materials that can bend light backwards. So depending on your epsilon and mu that you have, which is the dielectric constant and magnetic permittivity, if they are both positive, this is our normal material, conventional materials that we always have and we always study. So they basically, once from air it goes to the material, there is a refraction. So it just bends towards the incident light. Now here, if you have these plasma wire or fine wire structures, then your mu is greater than 0, but epsilon is less. So then there is no transmission and all the light gets reflected. So this is where epsilon becomes negative. So these are this is possible for certain frequencies with normal, right? Then you also can actually microstructure the material surfaces with split rings and all that. So where your epsilon can be 0, but mu can be negative. And again, there will be no transmission, and those structures will also throw the light fully out. But if you make metamaterials in a very specific way, you can have epsilon negative as well as mu becoming negative, and then your n becomes actually negative. And then your n, that is the refractive index, is negative, means if the light is falling in this direction, instead of bending, it will bend in the other direction. So you can have these kinds of ideas. So you can think about this. What happens if we put this some object in the path of light being, and what happens if we shine light on periodic structures like gratings, and what gives you a particular color, and why this band gap is there, etc. And basic idea is, can we replace electrons with photons? Because if you have a particular crystal structure, can we create similar crystal structures for photons? So basically, the answer is you have diffraction limits that minimum size of optical components. But now with these new type of things, you can go to sub wavelength features also, and these can be used by using microscopy. You can control these optical properties. You can couple light into and out of these nanostructures, and you can actually manipulate this light for its light emission, propagation, and absorption. So many of you have actually seen this peacock feather, and I'm sure this is some colorful beetle. So many of us have studied biology in our school, and they always said, oh, these are the different chemicals because of which these colors come in. While that is, I mean, sometimes it can be true, but mostly it is actually wrong. Meaning these colors don't come because of these chemicals. And I always had this question in mind that why this peacock feather has such a beautiful coloration, and when you move it, it also gives different kinds of shades. But that time I was of course told that it happens because of the chemistry. I mean those particular chemicals. Now actually let me tell you that that answer is actually wrong. It is doesn't happen because of chemicals. These are not chemicals, but if you see these under electron scanning electron microscope or ACM, you will see that these beetle, whatever structure that it has on its surface, is of these holes. Here, these peacock feather is consists of these planes of these proteins which are stacked over one another, and these are the ACMs of these. And you can also see a very minute structure here. Now, what does this structure do? And they are actually looking gray. And of course, in ACM, you see these as black and white, so they will be gray. But in reality, also, they would look like gray, and they will not look like this. But what happens is when a particular light falls on it, it changes its properties. And I will give you some flavor of that, why that happens. And this is also true of butterfly, because butterflies also have these, if you see their wings under the ACM, that high microscope, you can actually see nanometer or submicron features. These are sub-wavelength features which are created, these designs which are created on the wings of these butterflies. And this is all done naturally. It is nothing special about this. So these are all called, these are actually regular 3D periodic structures. And basically, this one was found by Professor Eli Ablanovic and Professor Sajeev John. He's from Kerala. He's now settled in Canada. And Professor Eli Ablanovic is in US. So they called what is known as a photonic crystal. So just like you have atomic crystals like sodium chloride or what is that, potassium bromide and all that, there the atoms are in periodic structure, and electron actually looks at this periodic structure, and then it gets diffracted, and that is how you have different properties of these materials. Similarly, if you, I mean, this is the idea which these people said, if we can have different refractive index of these materials, can we change similar thing for the photon? And the answer is yes. You can actually have just like electron waves in electromagnetic waves in the photonic crystals. So electron waves in crystals will behave exactly like electromagnetic waves in photonic crystals, or vice versa. So you can have reciprocal space, Brillouin zone, dispersion relation. You can have electromagnetic block wave functions. You can have photonic band gaps. And I will show you many of these effective mass and Van Wave singularities like that. So here is a typical semiconductor has a band gap. So there is an it is called, now I'm calling it as an electronic band gap. So there a particular wavelengths of light are allowed to pass, while some other are not allowed to pass. So if your wavelength of light or frequency of light or energy of that photon is higher than this band gap, then it is absorbed. It generates holes and electrons. And that's how all the photo detectors and everything works. Or all our sensors work. This is the basic principle of our sensors working. However, if you have a photon which has a lower energy than the band gap, then it passes through. So then you will call this material as transparent. So many times you will find glass, or it will look like a glass to you. So if you take zinc selenide or zinc telluride, these crystals appear to be either like white like or transparent like glass, or they look orange, or they look reddish or something, or sometimes they blue greenish, mainly because they are transparent to the normal light, and they only absorb light whatever color that they are showing that onwards. That means orange light will basically orange looking crystal will actually stop that light beyond the orange. So UV and everything else will get absorbed by that light. So that is why you are getting those kinds of colors. Now, similarly, you can generate photonic band gap with the periodic structure of different refractive index materials. And now those states which you are creating will be not allowed. So the photon will not be allowed to pass through that. So this is called the photonic band gap. And you can make these different kinds of structures, like these are called 3D structures, 2D structures, like this. And just like you have sodium and chlorine, you can have different in a refractive index material like this, and you can generate it. So you can have 1D system, 2D system, or a 3D system, which is periodic in all dimensions. But these are all materials with different refractive indices. So now you can see this idea is so powerful that you can now, take, these thin films, just stack them one over the other, and just choose an appropriate wavelength for that. And then you will actually start making a photonic crystal. So if for our visible wavelengths, this has to be of the order of nanometers, while if you go to infrared, they can be order of microns. And if you are working with like millimeter waves, then they can be of the order of hundreds of micron kind of thing. So which is actually thicker than our paper that you use normally. So there are, of course, slight differences. This forbidden gap is common overlap with all 4 pi steradian of space. So that means it is uniform all across. And the advantage of photonic crystals is it allows these index contrasts to be larger than 2. And you can also include electromagnetic wave polarization. So it can become polarization dependent. So here I will give you, this is a periodic line or cylindral lattice, and you can actually just remove one of this cylinder, and you can call this as a point defect. So now, if you remove the entire line, it will be a line defect. If you remove a point, it will be a point defect. If you remove one of the edges, it will become a surface defect. So you can do it any of these way. And Professor Gopal in our laboratory, he had done certain similar things. So now, if you do these kinds of removal of some of these defects, you can actually start confining light along one specific mode, and you can generate different kinds of modes. So what he did was, what Professor Gopal did was, he created this array of different holes. So you can see these are all periodic hexagonal array of holes, and only in certain region his hole shape has been changed. And what happens is, now if you put the light photon inside, this photon now actually can get split. So these are the simulations that were done to actually optimize these structures on the computer. And you can actually see some light is getting passed through, some light is completely reflected, and some light is actually split. So you can have actually what I call a particular wavelength dependent beam splitters, which are 2-dimensional. Now, using this idea, Professor P.H.J. Russell, who is from Max Planck, is the director of the Max Planck Institute in Germany. He was in England initially, then he shifted here. He did something more. And what he did was, he basically made all these, he put in all these different rods, or what you call the capillary tubes of things. And then he made a complete array of this. So now you can see, you can either remove a certain piece from here, or you can dope it with something else, so that it will have either different size, different refractive index, or some different kinds of things. A lot of things one can do. So these are capillary, pure silica capillary tubes. And you take this array and pass it through this oven, and then draw this, so they will melt basically, and then you can draw actually a fiber. So this fiber will basically have this kind of core, and then this hexagonal thing, and its diameter will be like few microns. And if you see, if you have everything properly arranged, then of course you have to calculate using the numerical analysis, that you can actually generate either a defect point, and you can generate a band gap. So this is the transmission through this. So you can see there is a certain band in which there is a the transmission has been block, so that gets absorbed. You can also do it in the reverse way. And you can actually, by removing one particular part, you can create a state, so only transmission will take place of that one particular omega naught. So you can have a very particular wavelength selective fiber transmission. So you can generate such type of fiber. So you can see, this is exactly, those who are familiar with physics of semiconductors will figure out that in the band gap you are generating one particular middle state, and this is exactly that what you are doing for the photon. So what is done for electron semiconductors is been done for photons in the photonic crystal. Now one can do this by doing a lot of computing. So there are large number of things one can do this. Now you will wonder, how do I design this? So because these kind of applications are providing all kinds of, energy, communication, metrology, imaging, everything, and everybody is looking for miniaturization, because you want to transmit huge amount of data. It has to be done reliably, the efficiency has to be good, and also it should take lower energy consumption. So all these, it is not possible for you to just sit and draw it and do. So all this has to be done by computing solutions. So what you do is, before even fabrication, you first model these, and these structures you actually run through computer and optimize them, and then only fabricate the finally optimized crystal or whatever that design. So there are softwares which can actually do this for you. And these softwares, for example, can do your band gap analysis of these photonic crystals. So you can see, as a function of wavelength or a frequency, you can actually generate different kinds of bands. So this is a three-dimensional band that has been generated with certain kind of features. So this is actually done for gallium arsenide pillars structure. And you will have different contrast, meaning you will have air and gallium arsenide. So there is a huge contrast, that you have air refractive index as 1 and gallium arsenide pillar refractive index as 3.5. And then you can actually see there is going to be a huge contrast change. You can also do this for optical ring resonator notch filter. So for example, you are passing the light through this. So you can see these modes are of the light are passing, and as soon as they come near this structure, this is a kind of structure that you have put close to, attached to the main waveguide. The waveguide actually couples to this, and then this is all done by computing. And you can see a particular mode is actually there is a standing mode, and you can actually use this for a whispering gallery. You can also create what is known as a hexagonal grating with these different kinds of structures, hexagonal structures. I'll talk about this, how we do this. And you can do this computation much before also. So for example, if you want to show your students, those who are teaching physics for third year BSc level or something, they can actually do these computations on computer using this software called COMSOL, where you can actually take a particular ball or a particular dielectric medium, and then see how the field lines go along it. So if it is a dielectric one, the field lines can actually go in, but you can choose that particular structure in such a way that these field lines will actually go out and again go in this fashion. Now this will actually tell you, if you look at from this point of view, for that particular frequency, this will vanish. That means you have created a cloak. So cloak means invisible ball. So this ball becomes invisible for that particular frequency. So all these kinds of things you can do by doing these kinds of things. So it will almost look like a magic to you. But this can be shown to the students. Those who are teaching, electronics and other colleges, engineering colleges, they can actually show them antenna structure. So this is the antenna, dipole antenna, and this is the field around it, and these are the field lines. So how the fields are going out. All these things can be computed, calculated, and can be shown to the students, so it can become very exciting for them. One of the students from VIIT Pune, Ravi Kesharavani, now he's joined GMRT. He actually designed this with Professor Chandrasekhar Garde of VIIT. So he basically gets these very nice students, and we have this collaborative work. So here he used from this console this monochromatic design using different mirrors, and you can see this is a very complicated thing, but you could actually see that the light is getting reflected off this grating into several different colors, and you can actually put the detector here and actually map out how these beams are falling on and where they are falling. There are so many different softwares that you can use, console, CST, micro, depending on whatever you are comfortable with, you can use this for this computational modeling software, because this doesn't need, this only needs a computer, and now all of you in your colleges or your institutions will definitely have high power computers. So there you can use this to design this. And I'll give you just one small thing about the whispering gallery mode. So what we did was we took one ball which was brought very close to the waveguide, and we transmitted our far infrared light through this. And we could actually, so this is our setup that was done by Himanshu. And you could actually see that this ball was brought in very close to this fiber that we made it in here. This is a microscope photograph. So everything is extremely sort of magnified, and you can see that the light was passing through like this, but at one particular point it gets coupled, and you can actually do this simulation in this console. It was done by Anushri, another very bright student from Mumbai University. Both are from Mumbai University. And you can actually put a small drop of some solution in micro liter quantity or even nanoliter quantity, and you are actually able to see standing modes for one particular frequency, and you can actually see that as a drop in the transmission. So one can do these type of things. Similar kind of work was done. Professor Kiran Kolwankar, I think he's also attending this talk. He had sent two of his students from Junjunwala College, Upasana and Bhagyashri. And they did a fantastic work of these using console. They did some patterns, their transmission. And you could actually see that for various frequencies, you could see some particular modes coming in into this. So I don't want to get into the details of this. But this whispering gallery mode kind of work has been done by Anushri and Himanshu. You could actually see the simulation results and the experimental results. They come quite close to each other, and they could actually show this. So similar things you can do in collaboration with us, because the computing power is easily available. And one can definitely use it for solving many of these interesting problems. Now we come to the nanophotonics, where the size becomes extremely small, and you can confine this light to a much smaller regions. Now here what happens is, in the nanoscopic scale, there are a lot of field enhancement that takes place. So many of these metallic nanoparticle doped glasses, some of you must have seen these photographs from, this is from this Notre Dame, Paris. That you see these vivid colors of these windows in their churches and all that. So all these actually happen because many of these materials in their nano form, their band gap changes, and they behave very, very differently. So if you look at the nanophotonics, there are a lot of applications you have. With these photonic crystals, I already talked to you about how one can do this, but with different nano size materials, you can actually have different colors, and they can be used in different dendrimers or plasmonic arrays, etc. And all these is extremely useful, for applications in solar energy, thermoelectrics, advanced storage, and many of these. So these are the very hot topics right now, where people would like to have them used for solving our energy crisis and all that. You can also use many of these, these UV absorption in the quantum dots to, use that for cleaning of these drinking water. And these are certain things you can also take energy from the IR photons of sun and also convert it. So nature actually is a very powerful manipulator and very efficient manipulator. By using all these nanostructures, it can actually have has designed. So for our eye, it has designed it very well. With all these microstructures, it can very efficiently collect light. Here, this light is converted into different colors to attract insects, or it can do photosynthesis. It can generate a lot of amount of vitamin D. Now, this corona or this Chinese virus, which is creating problems, you have already heard about this digital finger pulse oximeter. Now, this oximeter again, it has this small laser light into that, which is infrared, and then you have absorption spectrometer, which actually detects how much is the change in your so this light actually passes through our finger, and it actually being an infrared light, it passes through all our blood and everything. So it tells you how much is the hemoglobin absorption lines it monitors, and then it sees that if the hemoglobin is showing lesser oxygen content or a higher oxygen content, and accordingly it will give you that design. So now you see how much compactified it has become. You also have this pregnancy test, flow cytometry, and many of these things. Now we will shift to little next part, which is the particle plasmons, which again Professor Gopal works on these. I already showed you some of his work related to that part. So what happens is once you have a light electric field which is applied to these small particles which are smaller in size than the wavelength, actually they start, because of the electric field, they start oscillating. You generate actually dipoles in these, and these dipoles, basically you will have a wave that gets formed along this, and so there is a certain penetration in the field in the metal, and also, but they stay over in the dielectric part. So you can see that the light dispersion curve actually bends a little bit, and you what happens is basically you get this effective plasmon constant. So basically it's a wave of charged wave that gets launched along the surface of these metals. So you can actually have either prism type geometry or grating geometry, where you put the light, and then along a certain part, the reflected light can go this way, but you can also have light which can pass through along this. And this is possible because it is provided by the structured surface. So this is how you manipulate the structures and create these plasmons, and they have huge applications in biology, chemistry, metamaterials, microscopy, nanophotonics, optoelectronics, physics, sensing, spectrum. So a lot of things one can use this. It's very difficult for me to cover this, and because it's a completely separate subject itself of plasmonics. But I will give you one simple example of that you can actually do this kind of sensing by putting a small item on the other side with a very thin gold layer, where this reflected light, which is slightly penetrated below, here can start interacting with that particular chemical, and you would actually see that there is going to be a big change in the reflected spectrum. And this shift is very much proportional to the change in the refractive index. And you can see the change in the refractive index from 1.32 to 1.35, just 0.03 has caused huge amount of change, because these kind of changes are easily detectable in the nanometer range. Basically from 700 to 800 is a massive change. We have extremely sensitive wavelength change meters which can monitor changes in the wavelength. So you can actually monitor very slight changes even in the refractive index. So these are very, very powerful sensors. Then that brings us towards the sort of end part of the talk. So that's where I will tell you something more about what I actually do in our lab. So we do what is known as a terahertz. So this is the complete electromagnetic wave spectrum, and I already told you that you have right, the energy for the photonics applications going from these UV down to this even the up to the gigahertz region where you have very low energy. So the region that has been still unexplored is the terahertz region, and there one single photon has energy of like 4.1 milli electron volt. So it's a 1 terahertz is like 300 micron wavelength with one photon energy of 4.1 milli electron volt. So this is a very small amount of energy. So one can actually do material science using this and study different kinds of phenomena. So where it has been used or where it has applications are basically, I mean, here is a person who is standing with a newspaper in his hand, and this is the terahertz image of that, and you can see that he is actually hiding a big knife which is behind this. So terahertz can penetrate through his clothes and also the newspaper, and it can tell you that the metal is there because metal will actually reflect terahertz. You can also look at the different tooth. So it can penetrate through the enamel and actually can also show you X-ray like parts. But it cannot penetrate through our body or tissue because terahertz gets absorbed immediately by the skin because the water completely attenuates terahertz radiation. And here are different spectra of different materials, RDX, HMX, PET, and these are all explosives, and they have a very specific features or we call it specific fingerprinted frequencies. So just like our fingerprint is unique to us for a given molecule. They have a very specific frequency occurring in this. So that's why we call it as frequency fingerprinting. So many of these large molecules, they will have these rotational and vibrational energy levels in this terahertz range. So that's why you are able to detect them very uniquely. And they can pass through these materials through which the optical beams cannot pass through. So that's why they can pass through our clothes, but they cannot pass through our skin because it is very sensitive to water. So you cannot really use it like an X-ray. You can only use it for peripheral check. But all other like bags and many of these hidden items, one can actually identify. And that's why all over the world there is a race going on for the generation of high intensity terahertz. Because if you can have high intensity terahertz, then you can actually figure out, somebody carrying RDX, TNT, HMX, PET, and these are explosives. You can identify them at a long distance in those terrorists or those, they can be eliminated at a much farther away distance before they come close. So it becomes, that's why a lot of people would like to have these kind of scanners. You can also identify many of the drugs, contraband drugs also, if somebody is carrying. So this is the image of the shoe, and you can see that the backside is completely opaque. But through the terahertz image, you can actually see what is hidden. So there is a blade and other things which are hidden. And when you open this up, this is the visible image. So you can see that you can actually identify metallic structures and other plastic explosive structures because they show particular absorption in that. So here is the image of a person. He is hiding one pistol on his thigh, and one pistol at the back with a dagger. So this can be identified. So in TIFR, we actually did this imaging of leaf. So I can tell you that this leaf was put inside an envelope, which is brown envelope. So it was not visible. So once we scanned it, you can see that along the edge, the water evaporation is high, so there is a very less absorption of terahertz. But in the center, wherever there is a richness of water, there is a attenuation. You can actually figure out the veins of this leaf in both the cases. We also did this for Mahatma Gandhi's image, and you can see there is a watermark, but that watermark becomes visible only in the terahertz, and you can see Mahatma Gandhi's image here seen very quite clearly. This is of course old image because you can identify that from the 500 rupee note. So what we did was we used many of these ideas about the photonic band gap structures and photonic structures, which I explained to you. And we used it to generate high intensity terahertz. So we actually fabricated our sources of terahertz and everything right in India. This is my student. She now has gone to Finland. Deepa. She was from Amravati and very brilliant and extremely dedicated student. And she came from such a place that she didn't have any exposure, but she mastered this. This is one of the most difficult thing to do. That these are you can see 200 nanometer holes, which is a hexagonal pattern, and this is a 1 micron size. You can see. So there are about 6-7 spots which are lying in there. These dots lying in there. These gold dots. These are embedded inside the gallium arsenide thing. And this entire structure, she actually fabricated it on this. Is a master. She mastered this within a few months. So you're an exceptional student. And using this, we could actually generate and increase the efficiency of the terahertz emitters to a large extent. And you can see, I will show you that this is the spectrum of the photonic crystal that we created. So this gold with the gallium arsenide is like a dielectric and a metal. So you can call this as a two-dimensional photonic crystal. And we had to first simulate it, and this simulation was done, and we actually could see that there is a complete confinement of the field along the edges of these rods or holes. Yeah, rods basically. We also did for holes and many other things, but I mean here I am only picking up one particular application. So we did a lot of work on this. So here is the spectra that we computed on the using COMSOL like software, and you can see that we use actually 800 nanometer or 0.8 micron wavelength to excite this region. So we wanted maximum absorption in this region, and you can actually see that the reflectance has become zero exactly at that, and we have pretty broad absorption into that, because our pulse also goes something like equal Gaussian. So you have pretty neat absorption in that region. So as a result, I mean, you could see the enhancement near the edge field, and there was a heavy absorption, and we were actually able to generate quite a lot of terahertz. So it was also published last year. So similar such thing can be done, and also students who come from different backgrounds, I mean, given a proper opportunity, they can really do well. But they have to be really passionate and motivated about it, because she used to spend nights in the clean room to get the particular pattern done. I mean, it's very dedicated. We have also done similar work, I mean, some different work in collaboration with Professor Dattagupta and again Professor Gopal for controlling modes in these different structures for these. So this is called a metamaterial work. So I'll tell you very briefly that when you put light over these kind of structures, each of these act like an antenna. So I had already shown you the antenna or the dipole pattern that was getting emitted, just like that donut shape or medu vada shaped thing. So here you can actually look at the field pattern, and you will see that the excitation takes place. So this is a dipole that gets created here, and these two dipoles together can actually form a quadrupole, and that quadrupole can destroy the dipole which is creating at the L. So such a thing is possible to happen. So if you don't have these two rods, which are vertical rods, then if you just have one single rod, then what happens is, if you look at the spectrum will actually just simply go down, and there will be just one dip, because at one particular frequency only there will be a dipole that will get generated. But if you now additionally have two of these, then they generate what is known as a quadrupole, and that can destroy this dipole. So what happens is, now where there was no transmission of light, now you suddenly open up a window. So this is called electromagnetically induced transparency. That is, you have created a transparent zone with using these additional structures and manipulating their distance and all that. So all these things, of course, were first done on the computer. We optimized these, and only when we completely optimized, we fabricated those structures. So that's the reason you can see the RAID and the experimental simulated ones, they are matching quite a bit. We also did work on these hybrid metamaterials, so you can generate different periodic types of structures, and they will have basically, this is a theoretical and experimental measurements, and you can see that they really show very good agreement with each other. We also had this cut wire metamaterial, which acts like a band polarizer. So basically, if you look at these cut wire metamaterial and you rotate this with the terahertz frequency, so we have a terahertz which is incident on it, which is vertically polarized. So if you rotate this entire material through 180-degree or 360-degree, you can actually see that within certain regions you will absolutely see no transmission of light, and certain regions are completely transmitting. So you can actually have a polarizing, a particular band. We call it band polarizer. So for particular polarizations, it will not allow the terahertz to pass through, while particular polarization, it will allow full light to pass through. So this way you can actually create different kinds of materials which are actually not existing in naturally. So those students who wish to basically have opportunities of masters in photonics, or many of you who may be asked whether one can do courses in photonics and what would be the scope, you can tell them that you can do MTech or PhDs in IITs. There are also PhD in nanophotonics, nano optics, physics, and optical engineering. All these foreign institutes are there: Karlsruhe, KIT, Creole in Florida, Max Planck School of Photonics, Germany. These are one of the top schools in the world. In Australia, you have ANU University, University of Sydney, Adelaide, Institute of Photonics at Finland. That's where many of our students have gone there to do their further studies, postdocs, and all these. Many of them have got jobs. I'll tell you the next one. That is Denmark and NTU and NUS at Singapore. So ask them to basically focus on learning electrodynamics and quantum mechanics, because these are going to be the key things for photonics. Nanofabrication is very, very important. This is something which they have to master it. Of course, wherever it is available, they can collaborate and go there. So many of these ICERs, IITs, and have this nanofabrication facility, and they have to get themselves familiar with these characterization tools. There are also project assistant positions in national and international funded projects in IITs, universities, research institutes. So they can go for summer projects in there, and or have some collaborative projects, or they can do their projects like what Professor Kiran Kolwankar's students did with us, that kind of thing. This there are also jobs in scientific staff positions in BRC, ISRO, Semiconductor Complex in Delhi, Chandigarh, CSIR laboratories also hiring. And company-wise, there are these 3M, Global Foundries, Infinera, FFO, Nokia, Siemens, Emetech, ASML, Netherlands, Bharat Electronics. So many of these also accept, they need this, and progressively this number is going to increase, because now government is actually going for this Atmanirbhar kind of approach. So it is going to help increase high-tech industry in India right now, which is completely lacking. So this is all about those who are really interested in what what I'm doing. So our research, many of these I didn't talk at all. So we do a study of material using these near-field scanning terahertz microscope. It's of its kind in the some second or third in the world. So that we have developed here in India. We can do this. We are already beginning this experience. So I know I have built it, so I know this in and out. We also do terahertz waveguide, terahertz fiber designs. That's where you saw these. One part of it, which is the whispering gallery mode studies, but we have also done many other studies of these waveguides with different students for bio materials and protein studies. We are also developing analysis algorithms with VIIT students, Professor Watway and others. So they are doing their PhD on this. So because the analysis of these terahertz data is also still in the progress, because these algorithms need to be developed so that they can be used. We are also trying to have different terahertz crystals for the generation and detection. And we are initiating these optical pump terahertz probe studies in materials. And currently we are working under these materials under high terahertz field and materials under high magnetic field. So these are the ones which we wanted to actually complete, but because of this Chinese virus COVID thing, this is stopped. And final aim, of course, is for the development of terahertz nanoscope using STM. But this is, of course, my long-term dream. I don't know if I can do it, but all other things are already in shape. So I would give all this credit to these students. He's our scientific assistant, scientific officer now, Gajendra Mule. He is from Nagar, Sangha, Khodad, that is near this Narayangao. So if you know that place, so near Pune, and all others are. He is my postdoc, Arnab. So he's working partly with us right now still. Anushri and Himanshu will be working with us right now, but because of this lockdown, he couldn't come. All others have actually either completed PhD or postdoc, and they are all abroad. They did various things at various times. So I would give credit to all of them. And these are the things that we work on. So anytime you are always welcome to write to me for any ideas you have for collaboration or any students. So you are always welcome. So thank you so much for being here, attending this. It was a pleasure, and thank you to Professor Mahesh Shetty, Professor Shekhar, and Professor Gaikwad, and all the others, Bharatji, and many others who got a lot of people to attend this. So thank you so much. Yeah, over to you.
Thank you, Dr. Prabhu, for the wonderful talk, as well as giving guidance to our students and giving all the credit of maybe what you have done to your students. Okay, so wonderful. So we have few question answers. So I think Ketan.
Yes, sir. Thank you, sir, for excellent talk.
Thank you.
There are a few questions from participants. The question from Dr. Pallavi Raute:
Okay.
Is terahertz radiation is same as infrared radiation, or it's different in range?
Okay, the terahertz radiation is different in range. One can call it infrared, but typically the region which is between visible and this is where you call this as an infrared region. And terahertz is called far infrared because it has a wavelength of 300 micron. Typical infrared you will call for the light that falls between like 3-4 micron onwards up to say 15 to 20 micron, while ours is 20 micron going up to 1000 5000 micron. So it's up to millimeter wave. So this is the region where we work in.
Okay, thank you, sir. There are a few questions from Professor Mahesh Sethi. Is it possible to have photonic crystals by periodic variation in density of material, etc.?
Periodic density variation.
Okay, it was phononic crystal.
Phononic crystal. Yeah. People have made now phononic crystals, and they have come up with phononic crystals for the study of sound waves. So there are certain, because the idea is the same. You can actually stop certain frequencies of sound for a particular region. And this is possible to do. So that's a very nice question. You can do this. You can do this for any wavelengths that you can now imagine, because your now idea is very clear to you. You have to have some periodic variation of different, say, refractive index or some other material, and then you will exactly see the same effect.
Thank you, sir. Next question from Professor Mahesh Sethi. Since photons are bosons, as against electrons are fermions, can
Yes.
we compare photonic crystal with semiconductor crystals?
Well, 100% comparison is not possible. This is what I also explained to you. Because in the photonic crystal, one has to be a little bit careful about this part. Because here, I mean, you do have band gap, you have block wave functions and dispersion relations, you can have reciprocal space and everything. But there are this part. See, it is not simply a stop band, it is a forbidden gap with a common overlap in all 4 pi steradians of space. So that means in this is uniform across all. While for electron that is not the case, because it has a different mass and different band structure in different directions. That's the reason you have gamma, wx and all those symmetries. So it's a little bit more complicated than that. So I mean, you can have these 2 major differences. It will allow index contrast of this. So this kind of contrast in the atomic things may not be allowed for the. So that's the reason. I mean, if you create a superstructure or super lattice or some particular kinds of semiconductor, quantum well or some such thing, arbitrarily you cannot put 1 over. So, for example, over gallium nitride, you can't put indium arsenide or something. It will not allow those type of contrast. While refractive index contrast is very easy to, I mean, you can just have, so far as you have materials sticking to each other, that's perfectly fine. So these are some differences, and that is correct actually, as he correctly pointed out, the fermion and a boson. So it will actually do show some, but the basic idea you should get that there is a periodicity in atoms, and that leads to electronic band gap. So you will have a periodicity in the refractive index. It should lead to photonic band gap. Similarly, if you have density variations on certain particular part, it should lead to phononic band gap. So it's just a common idea that you can translate it across different fields.
Okay. Thank you, sir. And next question is it possible to simulate using fractional theory, or is it done as boundary value problem in electromagnetic theory?
First one was what? Rational theory?
Fractionals.
Rational. See, I'll tell you.
Fresnel theory.
Let us do some. Pardon?
Fresnel theory.
Oh, Fresnel. Okay. See, you can do this, but now I'll tell you something. I mean, just look at this crystal. Now I remove either this one or one particular line. Okay, and now I'll ask you. Okay, now you simulate. So probably you can do some particular theory, because there is a lot of periodicity here and except one line defect, and you will probably get an analytical answer. But now if I ask you to design this, I'm telling you it is impossible for you to come up with these kind of specific features in this fashion with these kind of values of these. See, this is a beam splitter actually, and this is a wavelength dependent beam splitter. And there are, you see here, these are very small, ellipsoidal or elliptical defects in here, and these are another set of defects. Now, how on earth you are going to figure this out? That how this will come? Because here you don't have any periodicity in this. Everything is broken in here. So here you really cannot apply those. So here you have to actually solve these numerically. And now that you have a computer which can do this job for you, it becomes much easier. I mean, you can tell the student, "Aure, ye aisa design karo, just put this it like this way, and launch the field from the left side, and look at what is happening on the other side, and keep doing this till you see something like this. I mean, this is not passing, but most of it is passing through, and that's it. Then you are done." So this also helps student develop his own intuition about certain ideas about what kind of structures will work in what way. So this is very important because these students are going to be the ones which are going to use so many machines very effectively, and if they want to really contribute very effectively, they must develop these kinds of intuitions. And because see, later what will happen, another 10, 20 years later, artificial intelligence itself will take over, and you tell them, "Oh, I have just designed a particular beam splitter with these specs." And that fellow will actually come up with some particular structure, and he'll tell you, "Oh, okay, this is the structure, you simply fabricate it and be done with it." But we don't want right now so much dependence on machine, because artificial intelligence right now is not that much progress. But you see, eventually, before it takes over, your student should go much ahead of that, because right now I'm telling you, these things were unimaginable to do without the use of computer for anybody. These are all designed by this. And I'm also going to tell you, actually today morning I had two talks where I actually talked about how things are changing in the world. I mean, basically, computing power is increasing so fast that now, last 10 years, the new materials like topological insulators and these wire materials and all these, which are very hot topic of study today, they were actually discovered or whatever by on computer. They were not made. They were made later. Once people said, "Look, these are the materials are possibly going to have these properties," you now fabricate. Previously, people used to fabricate, "Arey, chalo, ye periodic table le lo, pick up some number, this material, that material, put it together, make a crystal and do measurements." Now, that is not happening. That is all done by the computer. It will tell you this is what the answer is you are going to get. Is it going to be interesting to you? No, move. So like that, it will keep checking and come up with one particular material. And so people are now saying that with their computing power, with supercomputers at their hand, they are now specifying, "We want this property material. You tell us what material, what combination we should have." And now the computer has started giving that. So the great example of that is the room temperature superconductor, that lithium hydride, LiS6. This is completely made by computer. It said that if you have these materials in this kind of structure, you will get it. And how do you get this structure? That you have to apply 150 gigapascal or 100 gigapascal of pressure, then only you will get it. So all this is done by the computer first. He said, "This is how the room temperature thing will look like, and this is how under pressure it will look like. And therefore, you should apply the pressure, and then you will get high TC, which is at room temperature." And this is how they figured it out. And it was actually tested. So now here, computer is telling you what you should do and so you just specify. It's like, on an app, you tell, "Arey, wo pizza chahiye," or "I want ye idli batter." It's like that. Amazon delivers you. See, this is exactly, you are just specifying, "I want this.
Yes.
And people will tell you. So, I mean, of course, it requires huge computing power, but this is where we are going. And our students now have to know this, because otherwise they won't be able to compete with the world,
Yes.
So all this computing power has to be used. So Mahesh ji was right. Told me, you please specify something about the computer. That's the reason I put it, because these photonic crystals, it is impossible for you to design it just by sitting and doing some manipulation of calculations, this function, that function. Those days now are gone. Mostly people have very complicated structures, and they simply use this computing power to actually compute how the fields are going, because these are all time tested. So you don't have to worry or write down codes for it. You have to just design and then keep checking. So this is how it works. So
Yes,
does that
sir.
answer?
Yes, sir. Nice explanation. Next question from Dr. KG Bhole, sir.
Uh-huh.
Using metamaterials coating,
Yes.
then is it possible in near future to have clothes which will make us invisible? What is the current status of terahertz generating sources which can be used in wireless communication?
Okay, very good question. The answer to first question is there is already a cloth that one of our collaborators, Professor Anand Ramakrishna, is made, and they actually put it on the one of these airport hangars, and that became invisible to the 100 to 100 gigahertz frequency. So that has already been shown. So
Yeah.
that was also, I think, in the news also. So this has already been done and tested. But this is not done for the visible light. For visible light, you cannot really do it because visible light consists of 400 to 700 nanometers. So there is a pretty large variation of wavelength. And you cannot have really a cloak which can actually work for so many different ways. So one particular frequency you can do this, but not for all frequencies. So this is the answer for the cloak part. The second part is how much terahertz intensity and that part. So right now, the ones that we have generating in our laboratory and all that, these are all pulse sources which are in the microwatt range. However, if you want one single frequency terahertz, which are of course used by military, they can go up to several hundreds of milliwatt kind of thing. So they are still into the milliwatt range, not in the wattage range. So right now it is not going to be available for our public use. It will take at least 5 to 10 more years for these items to come, because military will then go to higher terahertz region with higher sources, and then they will pass on this to the public. So right now they will not pass it on. So right now, don't think that we will get it. Right now, you be happy with 60 gigahertz thing only maximum that you will get. Those will come in another few years. 64 gigahertz to be more precise, and those will be initially used in your D-Link or whatever that house Wi-Fi is there, no? So that will be used. So you can transfer 1 gigabyte files in 1-2 seconds. So it will be that high speed internally.
Yes.
But externally, you need to then upgrade your fiber optic network also, because right now you have only 5G, 5 gigahertz coming in, which is in the air. Eventually, this will go to 60 and all that, but for that, right now, high power source license has to be cleared by the American military, because they are not clearing it right now. So it will take some time. Always remember, these technologies are first developed by military. They use it only when they go next generation, then only they will transfer. Same thing they did it for internet. When they got this Wi-Fi internet at their level, what we now get it from 30 years ago, that time only they allowed us to have wired internet. So always remember. So they are have to be one generation ahead. So right now, for example, they are actually using, I mean, at least 15 years ago, they were using screens which are embedded in their specs. So all of you are using specs. Just imagine that to be a screen, and everything what you are seeing on your screen is actually projected on that. So that is something which they were using 15-20 years ago. So now they have cleared some of those technologies, so which will now be coming in into us. So now you will probably see everybody wearing specs and walking, and then they will have all the information of where they are. So instead of now using the mobile, they can simply see through their glasses without knowing. And the next level to that, which is already used by US military, is the putting a contact lens on your eye at the screen. So even you will not even have specs. So you will have, without specs, you will be able to see the I mean, it's a screen without the specs.
Yes.
But these advantages, these advancements will come after 5-10 years when they will go further more. So right
Yes.
now we can be satisfied with what we have.
Yes, sir. Thank you, sir. Next question is from Mahindra. How existence of metamaterials was determined?
How the existence of metamaterial was determined?
Metamaterial was determined. Yeah.
See, metamaterial do not exist in nature. The way we have to actually fabricate them by using this computing power. And there are, of course, several softwares which can do this, which I told you. These are the different softwares which are, available. So whichever ones that you are familiar with, you can use this and create a material which you probably will think that it can have these properties. So for that you will have to actually go through a lot of literature and see what are the designs people have tried and what are the new designs people are trying, and basically your computer should be more powerful to compute that in given time, because if your computer is not that powerful, it may take longer time. So that means you will take that much longer to come up with the appropriate design. So this is all basically a game of who has more computing power and who has stronger computing power. So all these metamaterials are designed now on that. So does that answer?
No, this question I think came from one of the slides which mentioned that metamaterials were predicted by a person.
No. They were negative refractive index materials were predicted by a person. That is at Vassalego. So what he did is that he said that if you can create this, these kind of periodic structures, you can actually this one. I mean, see, these are all theoretical possibilities. You can always have epsilon, epsilon mu greater than 0 is already everybody has seen. But this is also people have seen. So he said you can also have microstructuring of these and have it. And people actually found that yes, mu actually becomes negative. But then why can't we operate in this region as well as in this region? Why can't we have both of them negative? And the answer is yes, it is possible. But that time the technology was not developed that much. So they could not do it, but later they did it. In fact, to tell you frankly, Russians have done a lot of thinking on many of these inventions and new structures. They just that they are not really marketed well because of their socialist things, and all the Americans and others, they took credit. But actual original ideas have come from Russians.
Yes, yes.
I mean, they are not won Nobel Prizes in that much proportion, but all basic ideas, very novel ideas have come from the Russians. Very original.
Thank you, sir. Next question is, the way electronic waste is disaster today, is photonic waste will be disaster in future?
Right now, electronics
waste is disaster.
Electronic waste is a disaster. Whether photonic waste will be a disaster.
Disaster in future.
Well, that is a good question. It can happen, but what is happening is people are also now trying to figure out materials which are, environment friendly. Say, for example, solar thing, lead-based materials are exceptionally nice. Exceptionally nice, but because it is lead and it will basically contaminate the environment, they don't want to use it. They want to find out something much environment friendly. Otherwise, by now you would have had all the solar panels made of lead based things. So that is the reason people are not. So people are conscious also. I mean, those who are doing research are also conscious about this.
Thank you, sir. Next question is from Megha Yadav. Which type of laser is used in which applications?
Which type of laser is used in?
Laser. In which applications?
No, this is a very general question.
General question.
And so depending on your application in your mind, you can decide that particular laser. And normally the way you decide it is whether your application has use of that wavelength, or suppose you want to do some cutting, then you have to worry about whether it has enough power and all that. Suppose you want to look at the spectrum, then you have to see whether it has that much of band, or so there are different applications or requirements which will allow you to see that different parameter. So accordingly, according to that parameter, you have to match with that particular laser, and then only you can do it. So for example, you want to do communication, you can't use this green laser and other lasers, because the communication lines have to pass through this fiber, and fiber can only transmit 1550. All other wavelengths are actually absorbed. So 1550 nanometer laser will be perfect for that. So this question will depend on your application in mind.
Yes. The last question from Zoom chat box. Please explain what is nonlinear optics briefly.
Briefly, okay. See, when you have a particular light falling on our normal light falling on the material, there is an electric field of that light, which is actually relatively small in magnitude. So what happens is it actually goes in and starts oscillating these atoms or electron clouds, everything, and these electron cloud in turn emits this in phase. So basically this keeps happening, and finally that light comes out. Some part of it comes out, some part is absorbed, and some part is reflected. Now if you have this laser light has coherence in it. That means it's an extremely intense. They are having all in one particular phase, and its electric field because of that is very, very high. And now what happens is these electrons or these atoms or whatever material things, now they are very violently oscillated. Now previous one, which was a weak one, that had a small perturbation, but this has actually a huge deformation, and you can't, and it is not like a elastic thing like any rubber band. I mean, up to a certain point you can strain, but here what happens is these get strained much more than the required. So what happens is now it's no longer a linear stretching, but it is now getting into a non-linear stretching, and therefore it deviates from the linear one, and now you start having different kinds of effects. So now what it means is, because of these very violent electric field oscillations, you can now have emission of, not only just one frequency, but you can have, a double frequency also.
Harmonics.
So now what will happen is, mathematically the way you write it is, first initially you have polarization that gets created inside the thing, which is proportional to E. That is the first level of the electric field. And you have, actually it is not just first one, it has a series. So it is like chi1 into E1 plus chi2 into E square plus chi3 into E cube, like that. It's a series. Now if the E is very small, then you just have chi1 into E1 is equal to P. So that is simple polarization. That is what we all see. That's why you see light bending and everything. But when you go to higher level, you have now E square, E cube term, they start becoming dominant. Then you will start seeing additional colors of lights getting created, or additional photons getting created. And this is what we call it as a nonlinear, because now you are no longer proportional to the electric field, but now you are proportional to the square of the electric field or cube of the electric field or something more. So this is something now you start seeing. And that's what I mean, that it has gotten into a nonlinear region. So there is a complete theory that was developed by Nikolai Blomberg, and but that happened after the advent of laser. And then only people could actually do these experiments with intensely high field of the electric field. Yes?
Thank you very much, sir, for detailed explanation of each and
Thank you,
every question.
Kirtan. Just one question, Ragini. What is the success ratio between the model fabricated on a PC and the actual fabrication?
That's pretty large because I already showed you the experimental and okay, not here, but see, for example, this is what she did, and she computed this part, and this is the experimental one that we measured. So you can actually see that this frequency is slightly shifted, but that's okay. I mean, you already see the basic features of this. And this is very important because it saves you so much time, because we have already optimized it for this. Now, here
No,
this
I
is
mean to say, what is the success ratio? I mean, is it 100%?
100, I would say 80-90% it will be, because 100% is like exact match. One can do exact match kind of thing, but we really don't need precise match. We just need a match which can give you that particular feature. So, for example, I showed you this. So this work that we did with Professor. See, this red is a simulated structure, and this is the experimental. The black one is an experimental one, and they are now. I don't know what you will call this. This is, of course, I will not call it 100%. But 80-90% features are almost matching, because while in the fabrication there are many errors, and because suppose the refractive index value we have taken is slightly off, or the thickness that we measure is slightly off, then that can lead to little bit of changes here and there. In the simulation, you get precise numbers. No, 100 micron means it is 100 nanometer means 100 nanometer, 100.000. Now, in actual, it could be 102, it could be 98, it could be 95. We have no such control on this, because this is, of course, in the research thing. So we don't want this to move to some another region of band. So that will be completely wrong. That much is not happening. So this way, I would say 80-90%, and it is pretty good.
I think that answers the
and
question.
you will find that this success ratio is pretty high, and this is actually good.
Yeah. So thank
It
you very
saves
much,
us so much of time and effort, because we only put effort on this fabrication of this one.
Sure.
Yeah.
So now I'd like to call upon Mahesh.
So now
propose
I'd
the
like
vote
to
of
call
thanks.
upon Mahesh propose the vote of thanks.
On behalf of Mumbai Sub-Regional Council,
On behalf of Mumbai Sub-Regional Council,
I would like to thank Professor
thank
T. Ganesh
Professor
Prabhu for giving this enrichment lecture.
for giving this
Really this
enrichment
wonderful lecture, because wonderful, I would say, because we are really wondering
wonderful, I would say,
in what
because
direction physics is going,
in what
and
going,
for bringing out and exposing us to new concepts like data materials, photonic crystals,
materials,
glimpses
photonic
of the terahertz optics, and also very importantly, how students are contributing in simulation and predicting things, developing their skills in this modern technology.
Mahesh,
modern technology.
Prabhu sir, can you just put off your microphone,
Prabhu sir,
because
can
I
you
think
just
there's an
put
echo
off
effect.
Microphone, because I think there's an echo effect.
Oh, echo effect. Okay, I will.
Okay. Just yeah, Mahesh.
And then some glimpses of the terahertz optics and its application. Also, you gave a good number of research institutes where people can really work in this, and students can look forward. Also, teachers can motivate students to go to these places. We also thank all the participants, and of course, the KJ Somaya College and Physics Department and Professor Shekhar's team for hosting this IIPT online lecture series and making a collaboration with us. Okay, thank you all. Keep connected with us on the Telegram channel, as well as subscribe to Mumbai IIPT YouTube channel. Okay, over to Shekhar.
Okay, thank you, Mahesh.
Okay, thank you.
Thank you, Prabhu sir. Sir, please unmute yourself. What was happening? I think your microphone phone was picking up the
Your microphone phone was picking up the.
speaker voice.
I see. Okay, now.
Yeah, no problem. Okay, thank you very much, sir, for this wonderful lecture. And so we'll meet next Thursday for a lecture on Big Bang Theory by Professor Ajit Mohan Srivastav from IOP Bhubaneswar. Okay, so see you all at next Thursday at 4 p.m. Okay, and take care.
Thank you all of you.
And
Thank you
take care.
so very much.
Take care. Bye.
And Santosh, can you end the meeting?
Yes, sir. Yes, sir.